I don't know if
It's supposed to rain for a week straight.
Yeah.
Starting now.
Is that right?
Yeah, it's up until next. Oh, there goes. Oh, that's not right. Never mind. Still listening.
So we got about half a minute. All right, first question. I think the quiz is self-explanatory. If you want me to go through it, I will. The solutions are on OneNote. It's a couple of short dodge rules. The first one was at a 45-degree angle to the point it was going at, so you had to incorporate the sine squared of 45, which is 1 over square 2 times itself is 1/2 times 1.5 times p rad over 4 pi r squared. Then the second one is coming in normal, so that means the gain is just 1.5. And a lot of people made mistakes there. And when they did the aperture, it was lambda squared over 4 pi times just the gain, which is 1.5. And some people use the Fraser equation. You can do it either way, but the way I asked the questions, each answer led to the next. I mean, if you want me to, I'll go over it. It's pretty straight. Happy to. And I give you some problems. Any questions about the problems? This is radar related, right? Okay.
Actually,
Smith chart problem.
I don't have the questions with the, it was 8.50. It was using like the Smith chart and everything.
Yeah, I didn't get that one in.
All right. 850, you said?
Yeah.
What's the matching network, isn't it?
Right. It was a,
Design an open-ended shunt stub matching network to match a half-wave dipole transmitting antenna to a source with 50 ohm impedance. Okay. This is just to bring you up this, or make you remember what happens when you're doing stub matching. Y'all remember doing stub matching with antennas?
Yeah.
With transmission lines, you don't do it. Well, there's two ways of matching impedance. One is using elements like L's and C's, and the other is going ahead and actually putting a shunt stub in there, either open or short, right? All right, so here's the deal. We got a transmission line, and it's got a characteristic impedance Z0, which happens to be 50 ohms. It doesn't matter what it is. Then we have a load. The antenna is inconsequential. It's a half-wave antenna, right? So that 73.2 plus, or excuse me, yes, 73.2 plus J42.5. That means your load impedance here is 72.3 plus J42.5 ohms. Doesn't matter if this is an antenna or if it's anything, right? Okay, now when you do stub matching, the first thing you do, any kind of stub, and this is an open circuit, right? It isn't shunt, right? It says shunt stub matching. I think so. All right, so the first thing we do is find out what the normalized load impedance is, and that's going to be simply ZL over Z0. And so that's 72.3 plus J42.5 divided by 50, right? Y'all agree with that? I'm thinking the norm. I've got to normal, or I've got to take the normalized load impedance if you want to use a Smith chart solution. Y'all with me? It does say a half wave, right? And a half wave, if it's an exact half wave, you got the J42.5 there, right? Okay. Now, I don't remember, let's see, if it was 75 over 50, then that would be 3/2. So this is just shy of 3/2. If you can give me this, it's like 1.48 or something like that for the real part.
1.45.
Okay. Plus J
0.85.
0.85. That's your first point. And this is going to be done in parallel, right? It's shunt stub. That means we're going to be in the admittance domain. You'll get something like this on a final exam. So now I draw my Smith chart that hopefully you have access to. You've done these things many times. And here's the R=1 circle. Well, that's the normalized impedance. Because the stub we're going to put on is a shunt or a parallel stub, we're going to actually work in the admittance domain, aren't we? You all remember that?
Yeah.
All right, so now I have to take 1 over this to get YL, which is 1 over ZL. Does anybody have a calculator so you can give that to me? I can't do this in my head. If it was 1 plus J1, yeah, I can do that, but this I can't. It's a negative angle. It's 1 minus J something. I don't know exactly. Or not 1, but it's.
I got like 0.51 minus 0.3.
Minus J.3?
Yeah.
Anybody confirm that?
Yeah.
All right. That's the point you plot. Now, does anybody have a Smith? You got a Smith chart.
Yeah.
And you need a compass too, probably, and a straight edge, but just try to do your best here. So at 0.5, this is the R=1 circle, so 0.5 is somewhere out here. Are you with me? That would be the 0.5. And minus J.3 is going to be somewhere out here. It'll be like this. I don't know exactly where, but, and this is going to be your point, which is 0.5 or 0.51 minus J 0.3. Y'all see that? I call that really the first point because, I mean, you could call the conjugate point up here the first point, the Z, but you're going to go right to the opposite point. Now, this has a given radius, right? And the magnitude of that radius from the center is the reflection coefficient. You can read the angle down here if you want the actual angle of the reflection coefficient below. Do y'all remember this stuff?
Mhm.
All right, now you need to take a compass and you need to make a circle like this of that radius. Y'all with me? Now here's your first point. Now, there are 2 points that I can end up at. The first is right here. And that's going to be 1 plus J something, right? Right? Because you want to intersect the 1 circle. That's the idea. Once we got that, if we can get rid of that imaginary part, it's over. Because then when we denormalize it and multiply it by the characteristic impedance, we're looking into Z0. That's the idea. Then the reflection coefficient is 0. But there's also a point down here at the conjugate point here, which is 1 minus J something, right? And what is that something? Can you give me the value of that?
It's 0.8.
Okay. 0.8, and this is minus 0.8, right? 0.8. Okay, those are the 2 points. You asked about this. So does this make sense to everybody? Now we have to ask ourselves, first, what are the conditions? They want the shortest length, what, stub or line length? There's going to be some condition put on this.
Just says matching.
Nothing besides that.
It says determine the impedance looking into the matching network from the input.
Determine the impedance looking into the matching network from where?
From the antenna.
I'll just read the whole thing. So
Yeah, go ahead.
design an open-end shunt stub matching network to match a half-wave dipole transmitting antenna to a source with a 50 ohm impedance. Now suppose this antenna network is to be used as a receiver. Use a Smith chart to determine the impedance looking in the matching
Okay, wait a
network.
second. The source with the 50, read that again.
Design an open-ended shunt stub matching network to match a half-wave dipole transmitting an antenna to a source with 50 ohm impedance.
I'm assuming he's talking about a transmission line. There's a couple ways to do this. If it's just 50 ohms, all right, then we want the input impedance to be just 50 ohms, but it'll get there anyway this way. Just watch this. Now, there's 2 possibilities. If it's open, right, I want you to just go with me on this. if this is an open circuit stub, what is the impedance of an open circuit? Infinite, right? Therefore, the admittance of an open circuit would be zero. It means you would start right here. That would be the starting port if it was open, right? Now, if we're going around, we're going on the outer rim. These are all positive, J, right? If we want to go to this point, 1 plus J8, then we want to move all the way around here until we hit minus J 0.8, right? That's one solution. Or we can move from the load or from the antenna to this point, it would be 1 minus J 0.8, right? And then because we're going to add something to it, then we'd land there at the 1, excuse me. Then we'd want to be at J plus 0.8. Does this make sense to you? Now, I'm not sure which one he took. I'm going to go ahead and assume that he took this point as the distance to the actual, and I don't know, to the actual attachment point of the stuff, but it doesn't have to be. So if you come here and just shoot a line here, then your distance that you travel is from here to here. Do y'all see that, class? Did he do it that way? Does anybody know?
He has the open-ended stub length as 0.392 wavelengths.
0.392. Well, then he went to this one. Because it's a half wavelength, it's 0.25 is when you go from here to here, roughly, right? I'm going to guess he went to this one.
That one's 0.345 wavelengths.
What's that?
Negative 0.8.
Okay, let me go ahead and just make sure everybody follows what you're saying. What he's saying is if you shoot a line down here, right, there's a mile marker out here. And I recommend you look at the wavelengths towards generator, the outer circle.
Yeah.
Right, on the outer circle, what do you get as the wave number there?
0.345.
Is that what you guys got?
The stub length that he has.
Not stub length. I want to know what this point is. If you take that from the straight from the origin through the point 1 minus J 0.8, right there, where do you hit? Wait, what is it?
0.345.
0.345? Okay. Lambda. Okay, now, if you come down here, it's going to be greater than that. When you take this line and shoot it right from the origin through that point, now give me this wavelengths towards generator. What's that point?
0.44 is what I got.
Did you guys confirm that 0.44? All right, you with me?
There's a line.
Follow me on this. If we're going to do this method, this would be the stub length, okay? Not the length to the point where we attach, or, excuse me. No, this would be the point, the distance that we'd move to the attachment. And I'll just call this D. I think he calls it through in the book, right? Only he spells the whole thing. All right, so now, well, how far did we move if we moved to here to here? Well, you always go to the mile marker you land at, right? You all remember this? So you take 0.345 lambda and you subtract from it the mile marker you started at, just like on a highway, right? And that's minus 0.44 lambda, but there's something that bothers you. That's a negative number, right? So what do we always do? If we ended up with a negative number when we go to the place we ended up at minus the place we add half a wavelength. Remember that now? Have to add half a wavelength. So now we add 0.5 lambda. Now what's that going to be?
0.3 plus 0.405.
And that should be the actual distance to the attachment point, the D3. 0.405, did you say?
Yeah.
Yes.
So that's to this point right here. This D through where you attach right here would be 0.405 lambda. Now we've got to find the stub length, right? So we need the stub. If we went down to here, this is minus J.8, right? Now I'm not sure if this is the right solution. The more I think about it, the more I'm certain. I mean, if this solution Wentworth's one, this solution will work unless there's conditions. So now I need to get rid of this minus J.8, correct, everyone? So I start with an open, it said open circuit too, which is a little odd. Open circuit stub. That's got an impedance of infinity and an admittance of 0, right? Even when we normalize that admittance, it's still 0, right? Now, the 0 point is right here, correct? Now we want to move on this rim until we hit 0.8, right? I'm going to tell you, this is about J1, right up, right? And this could be the wrong solution. So if you move to here, you're going to see J 0.8, and the distance you move, this will start at 0, so just give me the wavelengths towards generator there. And we got it. Can you tell me that?
Yeah, we're at.
J.8. I don't.
A little to the right of that. J.8 would be about 0.1.
Lambda?
0.108, roughly.
Okay, so that means this is 0.108 lambda. This is one solution, and that would be the length of the stub right here. It would be D stub, 0.108 lambda. That's one solution, right? And
I don't have a solution for that.
I mean, this is one possible. It doesn't matter which one Wentworth chooses. Now, the other way to do it would be, instead of landing here, going from here to here, now we go from here to 1 plus J 1.8, correct? And then you got to get rid of the J.8, which means you start there and you go all the way to J minus J 1.8, right, class? Do y'all follow me on this one? This is sort of a final exam kind of question. These things, I don't usually put those on the first test, but when you're putting Smith charts and stub tuning into the problems, that's more of a final type of thing, because that's EMAG 1, 2. You're supposed to, on the final exam of this course, have elements from EMAG 1 incorporating the problems in EMAG 2, and this is from EMAG 1, this stub tuning. And a lot of people, you know, they need a little refreshing on that, so this is a good problem to do it. Y'all with me on this, on how you do it? Nothing tricky at all, but you have to have your head on straight when you're doing this stuff. You got to make sure, I'm in the admittance domain. Admittance is 1 over impedance. Everything's in parallel. If it was a series stub, then I'd be in the impedance domain. Whatever. All right. Did you have Wentworth? How many had Wentworth? You did? Okay, most of you guys did. Wentworth does a good job on this. I know that. All right. Other questions? That's a good question. Anything else? That's a good one. Did it answer your question? You have the solution to see what's up.
Not on me.
All right. Well, it's one of those two. There is another way to do this tuning that we're going to see later in microwave. And the way is by using both an inductor and a capacitor. And we can do it that way, but I'll show you that later. You get that in chapter 10. And that's the one that's a lot of times done because you can piece in an element and take care of it. But, you know, this tuning method I just showed you, that's in only one frequency. Whenever you talk about a, quote, wide band application, where they're going to have a center carrier frequency and a fairly large bandwidth, that won't work. Right, and that's something to keep in mind. It works for a very narrow, when those wavelengths don't move much. When they start moving like 10, 12, 15%, things fall apart. Okay, now about radar. I gave you a bunch of stuff with radar. Did you guys got any questions at all? Right? Transmitting power density, return power density. The time of flight I didn't cover, but we'll do that. We're gonna get through Doppler today too. I like doing a few other things with radar that aren't in the book, because I teach radar. Radar to me is very, very fascinating. I think I told you a little bit about this, but you know, radar has an analog in nature, and that's sonar. Bats, as well as dolphins, whales, a whole variety of mammals use sonar, where they create a sound, they transmit the sound, listen for their own echo. And their voice is unique, you might say, as yours or mine, and they can fly. I'm trying to develop a radar based on, this is going to be a target acquisition / search radar based on bats. But and I was amazed at this. Bats can fly in a very dense cloud of bats. They'll never touch one another. They can at the same time they can interrogate the area. They know where the cave walls are. They know where the other bats are. And if they see a moth, they can grab it. Now, if you think about the amount of signals coming, because all those bats are doing this, but they know their own. And they can tailor the actual voice signal, or that you might say their chirp signature, so that they'll get maximum resolution. First, they can focus their mouths, literally deform, sort of like when you go, something like that, where you're gonna focus energy, basically giving themselves high gain, and they'll have ears that deform, so now they're listening, like having a high gain antenna, transmitting as well as listening to the same area, without ever having what they're sending interfere with what they're listening to. It's an amazing thing. And these guys are chirping all the time. They're changing their signals. They knew when they sent what, and they get it back. So that's what I got really interested in, a lot of this stuff. And you know, one other thing with any kind of wave that's propagating and reflecting back, you get something called the Doppler effect in frequency. Y'all familiar with that? In a nutshell, what Doppler is a change in the perceived frequency because of motion. Now, if you ever been to a NASCAR race or been to a car race, when cars are coming at you, you hear, and then when they go by, you hear, because now as you're moving away, the perceived Doppler change in the center frequency is lower than the frequency as if they're coming at you. That's a perceived increase in Doppler frequency. I'm going to show you why that works. I love radar, and I love to tell you about some stories and how things you can literally build for yourself if you wanted to. If you want something like a motion detector, a real motion detector, where you're going to catch people, and it's not going to be light or anything like that, in your backyard or maybe deer. Anybody here hunt? If you've ever hunted, one of the things they have is motion cams and stuff like this. Well, how'd you like to know if there's anything moving out of that period? It might be a wolf, it might be who knows? But you can do this with radar. And the thing about radar that's unfortunate is it assumes that you can generate a signal and you know the exact shape of it. Did I tell you about your eyes, how they are radar? All right, well, we have what's called passive radar. I like to give you this spiel because it's important you haven't asked something you can grab at if you get interviewed. All right, now I'm looking around and I can see that's a fire alarm. I can see that sign. I can estimate, because I have binocular vision and I know the relative scale, the distance to the back door. I can do all that, and I'm not transmitting a thing. Everything is in the ambient environment. Well, in the microwave band, where most radar is out there, there's tons of radiation. There's Wi-Fi you can't imagine. If you look if you take a spectral analyzer or a network analyzer, put an antenna on it, wideband antenna, and sweep, you're going to see all sorts of transmitter frequencies. So there's a ton of ambient radiation in the microwave domain that's coming and scattering. The thing is, to train a radar to do what your brain does, where, oh yeah, I know that's coming from there, it takes an enormous neural network. It's not easy, all right? It's theoretically possible, and there are passive radars. But they assume that they'll do a frequency sweep. Oh yeah, there's one frequency there. Now we've got to figure out where they're coming from, so they'll slowly go ahead and interrogate the area. There's the likely source of that transmitter, that one. Then they can figure out by reflection, stuff like this, the likely path, you might say the most likely path that the actual signal took from the antenna, transmitting antenna, to the radar listening, and it's deflecting off of targets. This is a big deal with the military, but not just the military. When you're doing all sorts of stuff, when they're doing studies on wildlife and stuff like this, they would love to have this kind of, this available type of interrogation system where they didn't have to create the actual, you know, the signal where it's out. So anyway, that's called passive radar. And passive radar is of great interest to a whole lot of people, including the people that like Google and stuff that deliver packages. But right now, it's way out of reach. I mean, you don't have any idea of the amount of information they have to process and sort of catalog and figure out what's going on. Your brain does it like that. I can look at you. I know how far away you are. I can tell you the color of that cup. And it is done without me ever sending a signal, which is amazing. I just remember what I'm telling you. When it says, we are a marvelously designed piece of biomachinery, and they use all, they're not just kidding, it's unreal. So anyway, with radar, one of the things you can do, if you transmit a signal and receive one, you get a Doppler shift. So here's how Doppler works. So does anybody know how Doppler works? And I'm going to do the non-relativistic form of Doppler radar. There is a relativistic form of the, what I'm about to show you, this is Doppler frequency shift, but to be frank about it, unless you're talking about astrophysics, there's no real application. So I just stick to non-relativistic. And you guys haven't had general relativity or special relativity. You haven't had monitoring. So if we have a radar, this will be the transmitter and the receiver, it's monostatic. So the transmitter sends a signal and it hits a target. And the target is a distance r away. But you get the idea. Comes out, hits, reflects back. So with that in mind, we can say the total distance it covers is 2r. That should make total sense. If I send a signal and it comes back, it's going a total distance of 2r, right? Now the next thing we do is we go ahead and divide this by wavelengths. So now we know how many wavelengths we actually went out and back, right? Now we know if that thing's moving, there's going to be a change in wavelengths versus time. It should make sense to you. As the distance changes, the total number of wavelengths. So what we do, well, before we do that, the way Whitworth's book does, we multiply this by 2 pi, and now we get something called a phase. That's the total phase change the wave would have. Right? If every wavelength that goes 2 pi radians, we're going to stick in radians, right? Therefore, that would be the total amount of phase. You'd send a signal, the signal would hit, and that would be the amount of phase difference between what you sent and what you received. You agree with me? Now so I'm multiplying by 2 pi, so I have it in radians. Now when I take a time derivative of this, now I have 4 pi over lambda. Lambda is going to be just the frequency divided into c, the characteristic frequency. All right, c over f would be lambda. You could call it lambda naught because it's assuming motion doesn't affect this wavelength. Times dr dt. Y'all with me on this? Now, dr dt is the velocity of that target, but it's the velocity component in the direction of the radar. So if this is Vr, and it needs to be stated, that's the velocity component in the direction of the radar. Because if the target is moving this way, there is no change in distance right at that point, if you think about it. You all with me? If it's moving 90 degrees. So you need the component of velocity in the radial direction that's connecting the target to the radar that's transmitting. And now this becomes 4 pi divided by lambda naught times VR. And VR is the radial velocity of the target. By the way, it's actually the rate of closure. So, because if you have an aircraft in the air and it's zapping another aircraft, the apparent Doppler velocity is the difference in velocity between, the rate of change of the distance is how the distance between these two objects change. And when police are driving down the street and they're shooting you with radar and you're coming this way, the radar subtracts, they take into account their motion. So that speed is subtracted off from the reading. But they assume they're normal. They assume it's coming in at 90 degrees. They don't have radars that are called, that are really locational radars where they take a time derivative location. That would be extremely expensive. So they get this. And what is this? Well, just think about this. The time rate of change of the angle phi with respect to t would be an omega, small omega Doppler. That would be in radians per second of change. And that's equal to 2 pi f Doppler, or the actual shift in the Doppler frequency. So the Doppler frequency is equal to, if you look at this, I can divide 2 pi into the 4 pi, and I get 2. It's 2 over lambda naught, and I like to do it this way. And then it's times VR. Now that's the actual change in the frequency that was transmitted. So let me explain this to you as clear as I can. If you have something that's transmitting, and say the frequency is, 300 megahertz, then I have an object moving at me, and the Doppler shift is 100 kilohertz. That means that the actual change in the received frequency would be increased by the 100 kilohertz, which ain't much. Do y'all follow me on that? Yeah.
So this, like, if you're hitting something and that thing is moving, it'll actually change the frequency of the signal.
Of the received signal, absolutely. Because if you think about, if you can do this little experiment, or just go on YouTube and you'll look it up, Doppler shift. If you think about it, if things moving this way, well, your wavelength's this long, right? Free space or free time. As this thing's moving, all of a sudden, the whole wave hit over a shorter distance, so the reflected wave is crunched too, and it literally crunches the wavelength or increases the frequency. Either way, it will work. So that's the Doppler frequency. Remember, it always increases when it's coming at you and decreases when it's going away from you, or where there's an increase in separation between target and radar. Follow me? Let's just calculate this for something common. Suppose I have a radar. I used to give problems in miles per hour. We could, but I'll need Google to give me the actual meters per second speed, because everything in here is going to be in MKS, meters per second, wavelength meters, stuff like this. So let's assume this. Let's assume I've got a radar here as an example, and its center frequency of transmission is, say, 10 gigahertz. All right, that's X-band. And I've got a target out here moving in, let's say 200 miles an hour. All right, now the power of Google comes in. What's 200 miles an hour in meters per second? When I do this, I have to change hours to minutes to seconds, and then I have to take miles, multiply 5,280, and so I get that feet, and then
89.41.
okay. Tell you what, let's call it 90. So it's 90 meters per second. By the way, that's not that fast. It really isn't. 200 miles an hour seems fast. But when you talk about 90 meters per second, do you know how fast the 30-06 bullet goes? Anybody? It goes what? About 3,000 feet per second, or just shy of 1,000 meters a second, right? All right. 90 compared to 1,000, not much, all right? I'm just giving you scale here because there's a whole lot of stuff out there, jet aircraft, that travel a whole lot faster than that. They go supersonic. Matter of fact, there now have missiles that go about 1.5 miles per second. And it's very fast. The front end basically burns up if they don't have, they make it so, is my understanding, the front end of blades, it burns off, and they got enough there so before it hits, it's still got a little something there to protect it. But you won't believe how the atmosphere can ruin your aerodynamics at high speeds. You know what the SR-71 is, by the way? We're on this topic. That's called the Blackbird. It was one of the first biplane was, I think, the trying to think, U-2, and that got shot down. So they built one. This tells you about, you know, counter missions. They built one that's so fast, no rocket from the ground could catch it, no missile. It would have to be spaceborne. So it's called the SR-71, and it flew in the ionosphere at about 100,000 feet, I think. I don't remember the exact, it's probably classified. But when it flew, it was a dull red because of the thermal heating. And it was made of tungsten or titanium, one of those metals. And it was one of these things that literally expanded as it flew. It's out of service now. But that thing, the whole idea was they're going to see it. They're not going to see much of it. They're going to see it. The thermal signature is unreal. They can't do anything about it. It's a big deal. What are you going to do? Shoot all you want. You're wasting your time. But nowadays, with satellites and all that stuff, you've got weaponry in space. A different set of parameters. Now it's all stealth. And there was a degree of stealth on that, but now the fighters, I'll get into a little of that, are just about invisible to radar. Yeah, I mean, the F-35 is scary. It's got a radar cannon. There's nothing, you can see it with your eyes. From what I understand, I've never done that. All right, so that's 90 meters per second. Let's see what the shift is. Remember, it's a 10 gigahertz center frequency, all right? So here, first thing we need is lambda naught. Lambda naught is going to be C over F. F is 10 gigahertz, C is 3 times 10 to the 8th meters per second, divided by 10 gigahertz is 10 to the 10th. So that's 0.03 or 3 times 10 to the minus 2 meters, right? Now, when I look at this, the actual Doppler shift is equal to 2 over that, or 2 over 3 times 10 to the minus 2, right, times the velocity is 90. All right, that's 18, right? 10 to the 2, 10 to the 3 times 10 to the 3 over, so it's 600. If I'm wrong, correct me. That looks like it's 6, is that right? No, 6,000 hertz, right? You tell me if I'm wrong. Isn't that right, guys? That's 6 times 10 to the 3rd. I'm sending 10 gigahertz. If you looked at this thing on a spectral analyzer, you wouldn't be able to tell the difference. You can't see a target there. So when this signal's coming back, it's going to be at 10 gigahertz plus 6,000 hertz. Right? 10 gigahertz is 10 to the 10th hertz, right? You add 6 times 10 to the 3rd of that, it's indistinguishable. The only way they see, there's a couple of tricks they do. One is coherency, and if I have time, I'll talk more about that. The other is they take this frequency, and just like you learned about in your community, you had COM, are you taking it?
Taking it now.
All right, with COM, you learned about mixers where you take the carrier frequency and you multiply that signal that you receive by the carrier, ideally the identical carrier frequency, and you get a sum and a difference frequency. And the difference takes you down to what's called baseband. You all remember that? All right, well, that works, but not well, because the difference between to get a 10 gigahertz oscillator, that's exactly 10 gigahertz, and doesn't vary more than 6,000 hertz, it's ridiculous. I mean, just saying, a little bit of temperature usually would change it that much, right? That's an extremely small percentage. So what they do they do coherent signal processing. Are you familiar with that term? I don't know if I have time now, but I'm going to try to get into that. What it amounts to is this. Everything that they send, the signal they send, they keep a data record of that, all right? And the way, I'll get to how radar works really. Then they take all the incoming signals, and they do this in the digital domain. They have fast multipliers, and they multiply. What happens is the signals coming in, they take a data record of a certain length. It's got maybe 1,000 cycles, 10,000 cycles in it, okay, of the return. They take that, they digitize it, they put it in there. Then they wait about, a short length of time. They take another snapshot of what's coming back. They digitize it, put it in there. Then they do convolution. You know what convolution is, or correlation, either one. And they see the time delay between what they sent and what is received. And that time delay is what they use to gauge distance. Now, the speed for Doppler shifting is another thing, but it does use coherency. And I'll tell you, if I have more time, I'll get into this. I'm going to show you a little bit more about radar, but y'all follow me on Doppler? My real point is that amount of frequency shift is very, very small. You can't distinguish that just using have you guys used a network analyzer or any kind of a spectral analyzer? What you'll do is you'll have the power density versus frequency on this axis, and you'll see something, it'll spike up, and that's where your transmitting signal is. And the way it's doing that is taking a snapshot in time of the signal that you have on your antenna, and then it does you're feeding into it, a fast Fourier transform, and then scales it appropriately. Now, you all know what a fast Fourier transform is, digital Fourier transforms. They really allow you to do the same thing as a continuous time Fourier transform does, but in the digital domain, and they give you information very quick, a lot of information pretty quick. Anyway, you can't see this. The way you can hear a car change its engine revs, you can't. You can't use that same mindset when you're detecting things with Doppler frequency, when we're putting it in gigahertz, if their speed is 90 meters per second. But you yourself know, some of you probably got speeding tickets, cops' radar works, right? They'll get you. They don't get you just in an instant. They don't, boom, got you. It's not like laser, they won't. It's just reflected time. They send out a series of pulses, and they look at the rate of change of the reflection time. And then they know the round trip time from each pulse they sent. And they can figure out how far away you are for every single pulse. And then they can see the time rate of change of the distance. Then they can figure out how far you are. I mean, laser is going to get you can't break. But regular radar, K-band radar, the 33 gigahertz radar, that takes over a second. It's usually 1.5 to 2 seconds where they have to, before they can actually get a reading that's meaningful. And what it's doing, it's sending, receiving, and building this huge database that it can use and then correlate or convolve it with that. And I'll get into the frequency domain transforms. There's a thing called the ambiguity function. There you'll see the Doppler shift and the size of the target at the appropriate Doppler shift. And that does work very well. So I'm just going to tell you, there's a lot of math in here, and this course is not meant to get that far into, but I'm going to tell you a little bit about it. So now, a little bit more how a real radar works, okay? Because this is something that's important. Dr. Wimmerspook does not have this, because I don't know how many people that I've taught ended up working for the government or companies that do work for the government and work on radar. My graduate students, my undergraduate students that get jobs, And now with all these, the new automobiles have 77 gigahertz radar. There's a whole plethora of sensors, all based on radar that are out there. Motion sensors, I cannot tell you how many. So you're going to be immersed in it if you're an electrical and computer engineer, unless you're in sales. But I mean, really, it's likely you're going to need to know this stuff. So that's the reason I go a little bit further into this aspect. So here's the way a standard radar signal works. They take and they develop something, and this is in baseband, it's the low frequency. And this is all radar. So at baseband, what they do is this. You don't care about this that much about the signal strength. They're going to have a signal that does this. This is going to be low frequency too. This is with time. Now, this is just some voltage, V of D. There's 0, there's time. This can be an amplitude of A, but it's not really that important. It goes to 0 here. This would be the on time, tau, and this would be the period. It's called the PRI, or pulse repetition interval. It's a capital P. And the thing repeats itself over and over. Now here's the idea. When I'm transmitting, I'm going to take that and I'm going to modulate with a very high frequency signal, or multiply it. I'm going to transmit. Here's the thing I'm transmitting. As soon as I'm done transmitting, I'm listening. Follow me? Then I'm transmitting, then I'm listening. It's like up. All right, follow me? That's the way this thing works. So now there's going to be a high frequency signal. You multiply that with, then it hops on an antenna, it goes. And then when we get it back, we've got to strip the high frequency off, so we're looking at this. Now, if you think about it, if this is a radar, I'm just using baseband right now. This is my radar. And I'm transmitting here. Here's my target. It's a distance far away, right? Well, the first thing you have to do is find the maximum non-ambiguous range. And here's what I mean by that. If I send a signal down here, I'm going to be listening. Here's my receiving. This is V, call it VT transmitting. Here is V receiving of T. All on the same scale. Well, I sent that pulse. Then I received this pulse back. You get the idea. This is the same, we'll assume it's a stationary target roughly. All right? But there's a delay here, right? There's some delta T here, or TD. That delay is associated with the round trip time to the target. Do y'all follow me on that? You send a signal, it goes out, comes back. Then, if you're receiving and you're looking at this, then the very signal you sent is time delay. Y'all follow me? But what happens if the target is so far away that instead of being delayed there, the first pulse is delayed over here? That's your first. Now, you're past the range where already a second pulse is sent. Y'all follow me? So we don't know if this pulse or this pulse caused this return. Y'all with me? So the range, the maximum range that you can see something, it's called a maximum non-ambiguous range, is an important thing. And we use this for power, to figure out how much power we transmit and all sorts of stuff. And here's how it works, just so you get an appreciation. This isn't in Winkler's book. What we do is say the range, maximum unambiguous range. When you think about it logically, we know it goes out and back, right? That's how far we're going to go. It's the maximum. And we know it's moving at what? At the speed of light, right? So that has to be equal to C times the capital T or the PRI. That's the period over which the square wave repeats itself. It goes up, it's on tau, dead until it hits the period T, then it repeats, all right? So this is the maximum unambiguous range. If we don't get a pulse back in that length of time, we're about to figure, this is the range, but it's based on this cap T or the PRI. The maximum non-ambiguous range will be CT over 2, or really C times the PRI over 2. So I think your mind should be working right here, and you should be saying to yourself, well, how do you know where it came from? That's a good question. What you're going to do is radar power falls off as 1 over R to the 4th. Do you remember that? Just, you don't have to write this down, but if we talk about P receive over P transmit, that's going to be gain a transmitter, gain a receiver, lambda squared sigma over 4 pi cubed R to the 4th. Now that's just a basic radar range equation. R to the 4th. It's falling off real fast. So what you look at is the maximum size of the target you're likely to encounter out there. And then you take a look at the threshold of what you can actually detect in terms of power density. Look at this, how fast it's falling. If I look at this, suppose the transmitted power is known, the received power, the threshold may be, I don't know, maybe a nanowatt, something like that. Now I can back out of there the range if I know the maximum possible size of the target and the carrier frequency. You all see that? Because sigma is the RCS. So now I know the range. Now I can gauge what my T is, my pulse repetition interval. This is one way of back engineering. In other words, all this stuff is linked based on the size of the object, the frequency, the gains of the antenna as well. But I'm trying to give you some perspective on it. There's a lot more to this. I'm just giving you the basic. So that's the maximum unambiguous range. Now there's another thing that happens. When you're transmitting, some of you will have an appreciation for this. What happens if I have a target here and just slightly, suppose it's radars here, and I got one here. It's not quite, masking, but it's in the same radial plane, the same main beam. Y'all follow me? There's a distance, and this is called the range resolution. Look down there. This is the maximum unambiguous range. And there's also a delta R, and that's the range resolution. Now the range resolution tells you what's the minimum distance that you can see targets apart. Now this is important because if you have planes, when they fly in formation, the only reason it's a V is because they can't fly right behind each other. If they could, they would, but there's a thing with turbulence, air turbulence, so planes always fly in a V column. If you look at the Blue Angels, have you ever seen any of these guys do military exercises? So they always, and the reason is the radar guy at the ground can't tell if there's 1 or 100 or 1,000 because they're so close to one another in difference in range to the radar. The range resolution is violated, so they don't know if they have 1 or 1,000,000, and it covers the numbers. Back in the day of desert warfare, they taught armies to always walk the same tracks. So anybody that wanted to figure out the size of the army that went through there at night couldn't from the tracks. They all walked on each other, right? Kind of the same deal there with the military, and the reason they want all their planes packed near each other. It's not because it's safer, it's because there they can hide their numbers. And not only that, they can hide the type real well. Now, there's more to that. I shouldn't say they can, but aircraft are very hard to identify one from the other if you're a radar operator. You can't tell a C-130 cargo from an F-18, from an F-14 Tomcat, unless they're on top of you. You really can't. You can optically if you're looking. You know, a half mile away, you can tell if you got some, it's hard with a radar, very hard. So anyway, that range resolution boils down to this. We can prove this too. It's going to be the same form as that, only it's C tau over 2. And the reason it is tau is just the on time, all right? And the duty cycle, I didn't put this down, but I kind of assume you know this. When you talk about the duty cycle, that's simply tau over T. It's the percentage of time the thing's on. Typical duty cycles are between 10 and about 30%. All right, they normally are on, and the shorter the time, the better for range resolution. The problem is the average power goes way down when you have real short duration. You want a higher average power. There's a lot more to this. I'm giving you a little background on this because radar is fascinating. So anyway, that would be the range resolution, and I could show you how that works, but if you think of a standard pulse like this, where this is tau, right? Well, if you have two targets separated by distance, call it D, wave comes in, hits, and wave comes in, hits this one here. If you do the math on this, you got the first one coming in, hitting, then a reflected signal is starting, right? Boy, it's not easy for me to draw this. So maybe if you looked at just the reflection coming back at the radar, just as the thing hit would be like this, there'll be nothing. Then as the signal keeps coming in, it gets longer and longer. This would be the reflected pulse coming this way longer and longer. Now the pulse hits this, it's coming this way, coming this way, coming this way. You're going to find that the maximum possible distance you can get, so you have some dead spot between the reflected from here and here, back at that thing, will be C tau over 2. All right? And you can think of it where you want delta R, you know, 2 delta R here is the total round trip difference. You want that to be at least have a spatial deadness of C times tau, the on time. Think of it that way. Can you follow me on that, guys? All right. So that's sort of the range. This is range ambiguity or range resolution, and this is maximum unambiguous range. They're both important with radar. Since you don't have this, I'll give this to you. There's one other thing called the signal to noise. You've heard that before? You have in comm, right? Communications?
Yeah.
All right, well, noise, I better not go here. It's a function of bandwidth. And noise is something that has to do with the thermal temperature more than anything. You know how they do deep space astronomy work or anything? They use liquid helium to cool everything. So there is no shot noise, no thermal noise at all. And here's another story for you. It's that, I mean, we got what? Wednesday, Friday, and Monday off, right?
Mm-hmm.
We were going to vote on the test too. Let's vote on the test, and then I'll tell you the story, and then I'll finish up the lecture. So, anybody have any preferred dates for the first and only midterm exam? I've done it where I've given a couple of midterm exams and no quizzes, but the quizzes seem to work better to keep everybody on top. Any dates?
I vote Friday.
Friday?
We talked about it earlier. It's either Wednesday or Friday on that week.
It would be back.
All right, let's see, give me some dates.
Uh,
So it's Wednesday, which would be the Wednesday, right?
Yes.
Like the next class is gonna be an exam. We can do that, that's not a problem. Or
30th of the 2nd.
Friday,
Yeah.
all right, this is the 30th?
Yep.
June 30th? And this is July,
Second.
what?
Second.
July 2nd, because we have the 4th off, don't we?
Yeah, Monday.
Which
It's
is
actually the
Yeah, I think we get it off. Right?
Yeah.
We get Monday off?
Hope so.
Yeah, because July 4th.
July 4th on a Sunday.
We get a lot of days off.
Let me tell you about this. The federal government.
I didn't think about
saying
it. It's 4th of July.
Because, you know, they think, oh, it's a free day off. No, it's paid, all right?
Yeah, right.
I forgot about that.
I mean, these, you gotta understand something. You get people all the time they want it off and nothing gets done. The federal government collects us taxes, they do a whole bunch of stuff. They're supposed to take care of our roads. If we get potholes the size of, boulders out there, then you'll know who to blame. Anyway, I'm not a big fan of having just cajillions of paid holidays. If they're unpaid, fine. Well, I don't want to work. All right, so which of these 2 dates, we'll do it by a show of hands, and why don't you count with me, just because I might mess up. All right, if you want it Wednesday, June 30th, one hand, and hold it up. I see 1.5, 2. All right, you can only vote once. So if you want it on Friday, I'll raise one hand. All right. I'm gonna say the Fridays, yeah, we got one guy that didn't
We'll
show
count
up.
Austin.
What?
5-2.
Looks like a Supreme Court. All right, so Friday, all right?
Yeah, sure.
Now, I'm gonna tell you this much. If you're smart and talk to him, if you've had me before, use your head and do your homework and do what I say. Because if you do your homework and really understand, not just, it wasn't that problem. You didn't use 3 meters there, you used 2 meters. All right, if you really understand it, then you're gonna do well. But if you go piling through old exams, what's gonna happen is some days I cover certain things because of interest. Some days you're gonna get yourself really messed up. I've had kids say, there was none of that on the old exam. Yeah, and your point, it's like I didn't tell you to study the old exams for 20 years ago. I told you to do your homework and understand. I'm not joking about this either. We change textbooks, we do all sorts of stuff. Did you have me before? I know you did, Jacob. Have you had me or not?
No.
Anybody else have me?
No.
You have? All right. If you know anything about me, the homework's where it is. Because that's where I literally go through the homework. Oh, that's an important point. I'm going to make a problem up based on this. I change things a little, but I mean, it's basically the same problem. But boy, do I see some bizarre things, especially from people that are given to looking on, what is it, Chegg? Is it?
Yeah.
And there's they even pay people to do their homework, and they're clueless.
Yeah, right.
I don't know what you're trying to tell me, but it has nothing to do with the question.
I assume we'll be given homework over the break.
Yes, and I like in the past never to give homework. This is ridiculous. This is 3 consecutive class periods you're going to miss. I'm going to give you homework related to radar, and I can tell you where we're going next is EMC. It's 17 after we go through the bottom of the hour, through 2:30, right? I'm just going to tell you this. This is the next chapter. Right? That's the stuff you need to know about radar. I will give you radar stuff. I know people are anxious to get on. It's like a Friday almost. The next chapter, see, these are the 2 areas I work in. Radar and EMC, electromagnetic interference, electromagnetic compatibility. And the 2 are very related because with radars, you got so many things interfering. Oh, yeah.
So if we wanted to get ahead, are we doing that entire chapter, like all 9?
Yeah, but it's not bad.
But that's why I was making sure.
9 and 10, but I'm going to level with you. I mean, so far we've covered, quote, everything except fiber optics at the level I want to because they don't have cylindrical waveguides. If we have time to do it. But you got it. You got the whole 9 yards and everything. I haven't skipped anything.
Okay.
Yeah, all right, but I'm going to just tell you this. When you're dealing with EMC stuff, electromagnetic compatibility or compliance or electromagnetic interference, you're always thinking high frequencies. That's it. You're thinking high frequency and you're thinking wide band. So the first place we start is, what do wires look like at high frequencies? And you already know some of this. So when we talk about wires, a wire at high frequency, where we start is this. The change in resistance and inductance. So if we have a wire of a radius A, conductivity sigma, length L. And I wanted to know the DC resistance of this thing. Well, some of you know this. If it's DC, you can do it a couple ways. You can assume a current I here, right? And then you can take I and divide it by pi a squared to get the current density, right? Y'all remember doing this. I'm not going to do it. And then once you have the current density, you can get the E field, which is going to be the current density divided by sigma. Once you get the E field, you multiply it by L, you get the voltage. Then you take the voltage and you divide it by L to get the resistance. At the end of the day, I just did this in the other class, you get the resistance is proportional to the length, inversely proportional to the conductivity, and inversely proportional to the cross-sectional area. Here it's pi a squared. Do y'all remember doing this? We did it here too, didn't we? Didn't we do high frequency wires or not? We skin depth we did, right? Then we did high. All right, now, what happens when you get up in frequency? When all of a sudden the thing is skin depth, this is skin depth. I want to tell this. All right, I'll do it after. Skin depth is 1 over the square root of pi f mu sigma. Y'all remember that? So now that's the DC resistance. So now in Whitworth's book, he calls it RAC. But if you have the skin depth less than A, so now the skin depth is less than the radius of the wire, then what you have to do is figure out what the effective area is that the actual current flows in. So this would be a skin depth thing. Do y'all remember this? Now, the general way to do this is to say that now the resistance, this is RAC, when this is true, is equal to simply the length over sigma, and then it becomes pi a squared minus pi, and then it's A minus the skin depth squared. Now, if you look at this, that's the area that would be associated with the current equally spread over the cross section. But you have to subtract this inner course area off. That's why you have that. Y'all remember that, right? Mm-hmm. Now that's RAC if this is true. And then if and only if, the skin depth is much less than A, then we can say that RAC is equal to the length divided by sigma, and then it's just the perimeter. Then you can basically take this one skin depth thick, break it there, and straighten it out so you have a long piece of conductor that has a thickness of 1 skin depth, and its length this way would be, the perimeter would be 2 pi A, or the area would be skin depth times 2 pi A. So then it's times 2 pi A skin depth. And that's going to be the AC resistance when you get into high frequencies, or when the skin depth is significantly less than the actual radius. And by the way, this is the way it is most of the time when you have anything that's over maybe a couple hundred kilohertz. It's usually, you're talking about the wires could be hollow, it wouldn't change things. So now, well, what does the inductance look like? And remember with inductance, I think I talked to you guys about this, but I don't know. Inductance, you need to know the whole circuit. Didn't I say something about this in class? I don't remember if I did in this class, but here's the deal with inductance. When you have a wire, and I'm going to put it up here, maybe I didn't. Anytime you have current flow, you're going to have a magnetic field, and anytime you have a magnetic field, you've got inductive energy, and anytime you have inductive energy associated with a current creating, then, I should say magnetic energy, then you have something we term inductance. Just the way it is. So when you have a wire of a given length L, and you put a current I through it, and call this wire has radius A, I better put that in here. So it's got a current I, you could say it's uniformly distributed as before. And here's the deal. That current is going to give rise to a magnetic field. Outside, you could say that H is equal to simply I over 2 pi. Very lately. The bombs usually. Earlier. So anyway, that would be the H field if this thing was infinitely long. Do y'all remember that? That's a very long wire, and you're close to that's the H field. The magnetic energy would be this H field squared times mu. It's really, that would be the energy density. And you could integrate that around. But internal here, the H field isn't just I over 2 pi r. It depends on how much I is inside that region, right? That R distance. So I don't even bother with that. I'm just going to tell you this. The H field inside the wire is associated with the internal inductance. And the H field external to the wire is associated with the external inductance. Do y'all follow me? Now the internal inductance, we got that. So if we talk about internal inductance, usually it's called I in his book, internal, I think he uses, or L sub I. For DC, I don't know if you remember this, but the internal inductance was not a function of the radial distance A. That was per meter. It is proportional to length, but it is not a function of A, and that strikes, that should be shocking, but it isn't. It falls out because magnetic energy gets spread out, all right, in the same amount. So for this, it's going to be proportional to mu, all right, then it's proportional to the length, and maybe I'm going to do this per length. So internal inductance, it'll be per meter. So it's mu. Right, then it's divided by 4 pi, and in his book, I want to give you a reference page for this one.
I'll go for it.
I'm sorry. Yeah, it's in his book, it's 8 pi. He's gonna put it like this. It's mu 0 over 8 pi, and it's going to be henries per meter. Now that's what it is. I had 4 pi, 3 times a half, but just 8 pi. That's what it is per meter. So it's only proportional to the mu relative of the wire, not the radius A. It's just internal, not external. Well, this is per meter. All right. And here's the deal with this. We're going to get into this. There's this thing called partial inductance. When you talk about the magnetic field outside the wire in the external inductance, it depends on the return path. For instance, if you have a ground plane here and you put a wire over it, you image a wire opposite, and the total magnetic energy out of that wire around it is much, much less than if you just have a wire hanging in free space. Do y'all follow me? So the external magnetic energy is much harder to gauge. And there's a theorem called the partial inductance theorem that is in the center of the page. He shows this on page 505 that I'll talk about more later. But that, for now, I don't care about that much. This is the DC, and you better put this down. Put this DC for low frequency internal inductance. And that is what he has, this form, doesn't he? Right here.
Yes, that's on the,
All right, sometimes
or my,
you could see it different ways, but that's it. Now when you have something that is equal to, where now all of a sudden the skin depth is going to be less than the radius A of the wire, then you get the internal inductance. This is still internal inductance, but now it's AC, or a high frequency. This is still going to be mu 0 or mu over 8 pi. But then it's going to be 2 times the skin depth over A. And I think he might have it as mu times delta over 4 pi A, something like that. You see that? Yeah, this is equation 9.6, but he puts the L up top for some reason. So now he all of a sudden doesn't do it per meter. I like to always do it per meter, and this would be, again, henries per meter. Okay. Something to be said about this, that the internal inductance will tend to be just about 0 at high frequencies because the skin depth gets so small, you don't even worry about it. But the external inductance will always be something you have to consider because it's always has to do with the return path. I am just about out of time here, so now I'm going to finish my story. So long ago, y'all ever hear of something called Bell Labs? Bell Labs, Bell Laboratories up in New Jersey was the haven for Nobel laureates. And my master's professor worked there. I mean, they had the brightest and the best. It was like sort of a Google. Now, Google drafted pricing, but they had the best physicists and engineers, all were high paid, and they were always doing stuff that was way out the realm of normalcy. So they had, this is in the early 60s.